Thanks everyone for being here. I would like to welcome everyone to this webinar organized by Receipt and hosted by the CMCC on physical storylines of future tropical land precipitation changes under global warming. So Receipt is an ongoing project, 3 years now, funded by the EU, that is focused on mapping out climate risk storylines, typically by elaborating causal impact chains, detailing physical drivers, and cascading social and economic impacts. So my name is Raed Hamid. I'll be moderating this session. I'm doing my PhD at the IVM, which is the Environmental Studies Institute at the Vrije Universiteit of Amsterdam. And my work is embedded within Receipt, and I study compound impacts of weather extremes on crops and focus on the storyline approach to elaborate future climate risk. So I'll give a quick overview of a few technicalities. So our two speakers will give their full presentations, after which we will have a short Q&A session of around 15-20 minutes. So please feel free to drop in your questions in the Q&A box while the presentations are happening, and we come back to these questions in the Q&A session. So for the presenters, I will just give you a warning of 5 minutes and a minute before your time is up. And that's that. So now it's my pleasure to introduce our first speaker, Dr. Rohit Ghosh. So Rohit is currently a postdoc at the University of Reading, working with Ted Shepard on storylines of ocean-forced future tropical land precipitation changes from CMIP6 model simulations. Before that, Rohit also worked as a postdoc at the Max Planck Institute on understanding the Arctic influence of mid-latitude winter climate using multimodal large ensembles. Moreover, he also looked into understanding changes in the North Atlantic subpolar gyre circulations under future climate change using, again, large ensemble simulations. Rohit obtained his PhD at the Max Planck Research Institute, working on the impacts of multi-decadal variations in the North Atlantic SST on European summer climate. So with this, I give the word to you, Rohit, please.
Thank you, Raed, for a nice introduction, and thank you, CMCC, for this opportunity today for giving this webinar. So I would like to start. Hope you all can see the full screen.
Yes.
Yeah. So good afternoon, everyone. Today I'm going to talk about the work that I was doing in Receipt with Professor Ted Shepard from University of Reading. So this work is we try to understand the physical climate storylines of the tropical land. So first, I would like to tell about what's this, why tropical land. So in the Receipt project, we are trying to understand the remote climate impacts or remote climate effects on European regions regarding different sectors. So suppose we have 5 key sectors: manufacturing, agriculture, international cooperation, coastal infrastructure, and finance. So here I was mainly focused on the agriculture work package, and in this agriculture work package, the tropical land is important. In that sense, there are the 3 key hotspots for the 3 key commodities that we are evaluating in the Receipt are palm oil, cocoa, and soy. And the main region that Europe depends on for these 3 products are kind of in the tropical or subtropical regions for soy. So for, suppose like for cocoa, we depend on the West Africa, for palm oil in the Indonesia or the Maritime Continent region, and for soy, also in the Midwest US, and also in the Southern Hemisphere for Brazil and Argentina over this region. So what is the challenge? So in this project, me and Ted are trying to understand the challenges of understanding the future changes in the climate over these key regions. So the key stressor in these regions would be a drought situation or the extreme situation in the rainfall, which can change the situation regarding the growth of these crops that Europe depends on to get from these regions. And regarding that, the challenge first remains the uncertainty in what can happen in future over this region. So here I'm showing you a figure, a typical IPCC figure, where it's showing you the changes in the precipitation in the future from the present time. And this figure is from Zapaital 2021. So usually the full stipple or the stipple not the open stipple, the full stipples are the region where we are very confident what's going to happen. Confident in the sense that these regions show changes in the future in the same direction. So if you see green, it means the precipitation is increasing. And if you see brown colors shedding in the browns, you can see the precipitation is decreasing in the future. And the full stipple regions where we are confident the precipitation is going to change in a certain direction. Of course, you can see there are many regions in the tropics over the ocean where we are very confident, especially over the tropical Pacific, that all the models are showing in the positive direction change. But you can see in the tropical regions, or the three key regions that I was talking about that a receipt is focused on, we have open stipples. So the open stippled regions are, in the models, there is large uncertainty, but the changes are quite huge. So the positive and the negative direction, there is a large change, which goes beyond the changes that can happen from the internal variability or the noise in different model responses. So there can be a possibility that there is kind of a response present there, but as a mean, we don't find a clear response because they are going in different ways, either positive or negative. And I highlight here the three key regions that we are focused on, and you can see that those regions have this open stipple. So what I'm going to do, I'm going to talk about what can drive this precipitation. So what can drive this uncertainty? And from that drive, the knowledge of that driver and their connection to this region, I'm trying to show you some storylines of the future so that we can address this uncertainty and can get a future idea of what could be the future possibilities based on those drivers. So the first, my discussion and my method, I'm going to explain through focusing on this red region, which is the Maritime Continent. And then I will show the application of that method for West Africa and then for Southeast Brazil, which is another region for the last region for regarding the soil. So the first region is for palm oil production. So the challenge here that I was addressing is the forest fire. So the palm oil productions, usually the peatlands are cleared in many regions, and that causes forest fires. So the forest fires generate a lot of smoke and haze and kills thousands of people over this region, especially in Indonesia. So here you can see in the left the figure of the forest fire events that happens over this Maritime Continent region, and the red regions are the main focus. You can see in the southern Sumatra, southeastern Sumatra island, there's a lot of forest fires. It's showing in hectares how much forest fire happens. Another region is in the middle, is called Kalimantan. So this Kalimantan region also sees a lot of forest fires. And also in the eastern side, you can see the Papua island. In the eastern side of that island, there is also a lot of forest fires. So these are showing the burnt area from the record on Tropical Peatland Society. And in the right side, you can see a figure from NASA, which is showing forest fires in 2015. That year was a strong El Nino year. And during the El Nino year, strong El Nino events in the Tropical Pacific, we see the severe forest fire events because El Nino usually bring more drier conditions over this Maritime Continent region. So this is called the dry period because climatologically during this period, the rainfall is lesser than the other half of the year. So I will try to first show you what are the possible drivers. As you can understand that the first driver is the Tropical Pacific Ocean as from the El Nino. So here next slide, I am trying to show you so first, before going to that, first I try to show you the uncertainty in the rainfalls in that regions before going to the drivers. So the first, for the uncertainties, here I'm showing the changes in the future from the past. So my past is the climatological mean from the couple model intercomparison project 6 models from 38 couple climate models, which ran for the historical periods from 1850 to 2014. And then they have scenario runs from 2014 to 2100. So I have a past climate, which is an average of the climate of 1930 to 1960. And I have a future climate, which is the average of 2070 to 2100 from the worst case scenario of SSP 585 scenario where we don't take any action to mitigate the climate change. So here you can see the differences. So you find these key differences in this region. This is the multimodal mean, as I have shown you previously, that there are large uncertainties. So regarding that, first, this Sumatra region, you remember from the previous figure, has shown a lot of forest fires, and you can see the uncertainty in the future precipitation in that region. So on average, you can of course assume that the rainfall will be in the negative side, but you can see how much strongly negative it could get. It could also reach -4 mm per day as a mean over this dry period, and also go to +2 mm per day. So similarly for Kalimantan, you can see also similarly the uncertainty in the rainfall, which can go in the negative direction to much higher in the positive direction. And also for the other region that was in the New Guinea region, you can see that the rainfalls are mostly in the positive direction, but it also have uncertainty, but not as high as the key regions of the forest fire regions, that Sumatra and Kalimantan. So now talking about the drivers that I was mentioning before, this is the main drivers that I will consider here is over the tropical Pacific. So in the tropical Pacific, here I'm showing the sea surface temperature variability in the observed record. So the observed record here, I have considered the Hadley Center SST data, and I have performed an EOF analysis to show you the first two modes of the EOFs. And in the first mode, it's capturing the ENSO, and the time series here in the middle of the first PC1 is representing the time series of the ENSO index. And I highlighted this region is kind of showing you the warming throughout the Equatorial Pacific Ocean. And the second mode is showing the long-term changes in the Pacific Ocean, and you can see it has a warming in the western side, and there is a cold tongue from the eastern side to the central Equatorial Pacific. And it has a time series which is going upwards with time, which means the western side of the Pacific is warming in the observations, while the eastern Equatorial Pacific is cooling. And if I want to understand what is the response with respect to this kind of changes in the SST in the Pacific Ocean, we can regress these PCs to the precipitation in the dry period, and we can see that that we already was mentioning that the ENSO index, when it's in the positive phase or in the El Nino phase, we have strong drying over Kalimantan and also southern Sumatra, the key regions for forest fires, and also over the islands of New Guinea, Papua New Guinea. So it has an overall drying response. And in the second mode that I have shown, which has this long-term change, capturing the long-term change, you can see it has a wetting response. Of course, if the ocean around the Maritime Continent is warm, we would expect more rainfall over the Maritime Continent. So it's dynamically consistent also what we expect from this kind of patterns. So now I will focus in this region. So I will consider basin-wide Equatorial Pacific, BWEP, as my one driver of the Pacific Maritime Continent rainfall. And another is the difference between the Western Equatorial Pacific and Eastern Equatorial Pacific as another driver. So one is capturing the gradient in the changes in the gradient in the Equatorial Pacific, and one is the basin-wide, the total change. And I will try to see what are the effect of the climatological change in these regions of precipitation on the uncertainty and the precipitation that we see in the Maritime Continent. So first I'm showing, I've got the average, made the difference, future minus past, and I'm showing how it's uncertain in different models. So this box plot shows this difference of the basin-wide warming, which is in the left side box plot, in different models, the spread of that, the uncertainty. So some models show only close to 2 to 2.1 degrees Celsius change in the average basin-wide warming, to some models can also reach above 5 degrees Celsius warming. And this all changes, and here you can see the global mean surface temperature changes or the climate sensitivity. So some models shows a change of 2.5 to 6. So and the right side, you can see the gradient change. So mostly you can see the models change in the negative direction. So the negative direction means mostly in the models in the future, the equatorial eastern part is warming more, which is opposite to what we are seeing in the reality and observations in the last 100 years. And there are also some models, of course, which also shows the western side is warming, which is in the positive side of the scale. So here is my drivers, and we are also having the climate sensitivity, which is different models as a whole warms in different levels. So to separate that effect, that is the thermodynamic effect, would come into that signal. So we would scale our drivers with that thermodynamic effect. So I have these two drivers, and then I will scale it with the global mean surface temperature to represent the basin-wide Equatorial Pacific change with respect to equal 1 Kelvin change in the global temperature. And here in the next figure, I'm trying to show that what is the effect of that as a whole to represent what happens in the Equatorial Pacific. So the spatial structure of that difference. So how that uncertainty related to the spatially, how the SST looks like. So that's what we expect, that the basin-wide Equatorial Pacific should represent a basin-wide warming, and with west and east Pacific minus will show the pattern with the western side more warm to the eastern side. So it's kind of showing you what we expect. So now if we try to understand, to see the spread in this run, so I have shown you the box plot, and here I'm showing you the same in a scatter plot, where the y-axis is showing you the basin-wide SST change, and the x-axis is the gradient, the western Equatorial Pacific to eastern. And you can see from the scatter plot that they're independent, they don't relate to each other. So they have no correlations in the models during this dry period. And in the color coding, what I'm trying to show you is those models which show a more western Equatorial Pacific warming, which has happened in observations until now. And the red colors, I'm showing the models which show warms more on the eastern side. So there is large uncertainty from this figure that you can realize. And how this uncertainty relates to the precipitation over the Maritime Continent could be understood if we do, again, include these two factors in a multiple linear regression model and try to understand the links to the precipitation. So that's what we try to do here. We form a multiple linear regression model following Zappa-Shepard's method that was applied for the mid-latitudes. We apply the same method for in considering these two drivers. One is the basin-wide warming and one is the gradient. And it's a simple multiple linear regression model, and we will see how they relate through these coefficients B and C through the precipitation over the Maritime Continent. So here you can see that every signal is divided by GMST to separate or isolate the signal that would come from the thermodynamic warming, and from these dynamic drivers responses we can understand from B and C. And to see the patterns, so here I'm showing you the B and C coefficient patterns, the spatial patterns, which shows the relation of that driver through to the Maritime Continent rainfall. So the striking part is that the basin-wide Equatorial Pacific warming, showing you the drying regions over the same region that has high risk of forest fire. So the southern Sumatra and the Kalimantan, and also it has response over the Papua region in the eastern side. So it capturing these three regions, which has shown in historical period has a sensitivity to the generating more dry conditions. So of course, in the models which has warmed more in the basin-wide Equatorial Pacific has more drying over this region, and correspond to the model which has less warming in the basin-wide. And in the west to east Pacific difference, so the models which are more warm in the West Pacific, we see, of course, a higher rainfall that we have also seen with respect to the connection in the observations, how it connects to the region. So here you can now, the patterns of the relations are complementary. You do not see any response, significant connection to the eastern side, to the western side with the west to east Pacific difference. So based on these connections, we can build storylines. So the storylines will show you the future states that could happen. So usually in the multimodal mean, you see a storyline that is at the middle of the scatter plot. And in the storylines, you would see, based on these driver situations, storylines. So in the x-axis in storyline 1 is showing you a storyline where the basin-wide Equatorial Pacific would warm more than average, and there will be more warming in the eastern Equatorial Pacific than the western Equatorial Pacific. And then similarly in storyline 4, you will find another kind of storyline where the Western Equatorial Pacific will be more and more, and overall the basin-wide Equatorial Pacific would have warmed less. So how the picture will come with respect to this kind of 4 storylines is shown in the next slide. So in the middle is the multimodal mean figure that I have shown you in previously, but there could be a situation in the A plot that you can see where the storyline would be, if there is a higher basin-wide Equatorial Pacific warming, we can find a very strong drying response over the southern Sumatra, the key region for forest fires, and also over the region of the Kalimantan. So this can increase the risk for forest fires. Although in the observations, we find that this the Eastern Equatorial Pacific is not warming more, but until now, the Western Equatorial Pacific is warming more than the eastern side. So that leads to the storyline E, or the storyline 4, where we have a picture of more rainfall happening and not much change happening over southern Sumatra. So the risk would be less. And also the cross situations are shown in B and D, which where you in general, if you see if there is a basin-wide warming is more, you have less rainfall over this southwestern part of the Maritime Continent. So in that regard, I try to summarize this part. I explained the method. So what we could understood is these 2 tropical Pacific SST drivers, how their states in future, how they can lead to different kind of precipitation responses over the Maritime Continent. And we also got an understanding that if our basin-wide Equatorial Pacific warms higher, then we have a more drier Maritime Continent, especially over the forest fire, where the forest fire happens. And we could construct storylines based on these responses from this multiple linear regression model. We can add it up and then show a future based on these drivers. So if we have any questions from this part, we can also take at this time, or I can go to the other parts. So we are in the middle of section, and then I will show next for the West Africa and also for South America, for the Southeast Brazil.
Rohit, so far, no questions. So I encourage people to just put in their questions in the Q&A. And so you have also 10 more minutes for the second part. So just that you
thank you
yourself also.
Yeah, so that's good that I can. So now the method is kind of, I think I have explained the method. I can come back to it later if it's needed. But I can go for the next part, where I am showing you the cacao dependent West Africa. So here you can see the cacao region that the EU mainly imports cacao. So it's the data from Eurostat web page. So where it's shown the cacao that was imported in 2016. So 3/4 of the cacao that EU imports is from these 3 countries. It's 1.7 million ton of cacao that the EU imports in total, and 3/4 of that comes from these 3 countries in 2016. And also a holistic picture can be like a broader region, how the cacao is grown in this region can be seen from this figure from Merem et al., which is showing the annual production in tons, the cacao. And of course, you can see that these 3 countries stand out, the Ivory Coast, Ghana, and Nigeria. But also there are other regions, Guinea, Liberia, which is also having cacao productions in some level, and Sierra Leone. So I will keep these driver responses that you have understood. I'm focusing on the tropical SST or drivers until now. So I will show you the uncertainty in the precipitation over this region. So this is the multimodal mean difference, future minus past, during the summer period. So the summer period has the most uncertainty over this region, the open stippled regions that I have mentioned before. And you can see the uncertainty in the West African rainfall, which can go into the negative values until more than minus 1.5 to positive values over 2 mm per day. And if here I will consider 2 main drivers. So I have again the basin-wide Equatorial Pacific, which I have before, but these gradient drivers I replaced with a more relevant driver for this region, which is the Tropical North Atlantic Ocean SST. So Tropical North Atlantic is the SST basin just below that region, which is also known as Gulf of Guinea most appropriately. But you can see now the response patterns that I have built before with the MLR. So you can see that with the basin-wide warming of the Equatorial Pacific, you have a drying response with a significant drying in the western side of the western coastal side of the West Africa, and with the tropical North Atlantic. So you can now understand the driver region is just here where you have this possible positive rainfall anomalies explained through the SST anomalies quite confidently, and also that anomalies goes inside in the eastern side where we have this strong dependence on the countries mainly producing the cacao. And based on these responses, we can again build storylines, and I highlight the two extreme storylines that can happen based on the future states of these two drivers. So in the middle, you have the multimodal mean, which has not any clear response, but it can be much more better if we have a higher tropical North Atlantic SST in the future with a low warming in the basin-wide Equatorial Pacific. And we can have also another picture where we have a very strong drying over the entire region where the cacao produced mainly when we have a low tropical North Atlantic warming and a very high basin-wide Equatorial Pacific warming. So these are the two future storylines, extreme storylines for West Africa. And then applying the same method for the Southeast Brazil. So for the Southeast Brazil, so here I'm showing you the main soya producing region. So this figure I took from Brazilian Institute of Geography and Statistics page. So they are showing the difference in the amount of the hectares harvested area of soybean that changed from 1980 to 2017. So you can see this key region that's coming under now producing more soya because of the increasing demand with time. And I will focus on mainly the planting and the growth season. So here you see a chart from the cropprofit.com. I got this chart for the soya. There's a three part when the soya is planted, and then there's their growth in the gray area and the harvested. So the planting part is the spring period, the October, November, December. You can see Brazil soybean in the third column here. And also it's important for Brazil corn, but here our focus is soybean. So I will first show you the storylines that I'm considering, the drivers that I'm considering for here. First, showing you the uncertainty. So this is in October, November, December, the soya plantation period. What is the precipitation looks like here? It looks strong drying because I'm keeping the same scale that I'm using for other regions, but it has also uncertainty. So you can see that there is a strong, this precipitation can go until minus 2.6 to the positive side above 1 mm per day. So there is also a strong uncertainty in precipitation over this region. That's mainly during the plantation period. And for soybean, I am considering these two drivers. I'm again keeping my basin-wide Equatorial Pacific the same in the left side. But for this region, there is another very crucial driver, which is the subtropical South Atlantic SST, which controls the tropical convergence zone over this region, which controls the rainfall. So you can see the uncertainty in these two drivers here in this figure, that how much different it could be in different models, how much differently it could change. And you can see now what its effect is. So you can see the effect of the basin-wide warming, which is not really significant over this region from the models, but the main driver that you can see, the uncertainty in the subtropical South Atlantic, explains the main uncertainty. So when the subtropical South Atlantic is very high warm in the model, in those models, there is very strong rainfall over this region, corresponding to the model where it changes but not so much. So we have the opposite effect. So if we consider these two drivers and makes the two extreme storylines that I have shown you before, then you can see these two different pictures of the future. So in the multimodal mean, it's showing you this picture, but in the model where the Equatorial Pacific is not warming more, and there is more warming for subtropical South Atlantic, you can see a more wetting situation corresponding to mainly if you have a low subtropical South Atlantic warming, then we have a very, very strong drying situation over this soya planting period. And then I have continued if I can add just the same analysis just to show for the growth period, where strictly speaking, it should be January and February according to chart. But I have in the early plantation period from October beginning, there are some areas where the growth period could be also still December. So I have a mean here showing for the same thing for the December, January, February. So you can see the multimodal mean difference and the uncertainty here. So the same analysis that I was showing for the plot before, the uncertainty range and the precipitation still highly uncertain, and the same two drivers. And with respect to that, you can see the precipitation still, the basin-wide warming has not so significant response, but there is a kind of response still remains from the South Tropical South Atlantic SST driver, which together can still bring more drier situations in one storyline where there is a high basin-wide warming and there is a low South Tropical South Atlantic warming. Then we can see a more stronger drying compared to the other side, that you can see a completely different picture for the future. So these are the possible storylines apart from the multimodal mean, which is mixing the signals and giving a mixed picture of what could happen. So in that note, I would like to conclude that what I was trying to show today is first, how the uncertainties in this oceanic driver evolution in future can connect to the tropical land precipitation. So the tropical land precipitation could be different, depend on how this oceanic driver evolves in the future. For these three main regions, that was the focus for the RECEIT project. Sometimes from this analysis, we also understand some potential dynamical connections, like for Maritime Continent, we have seen how basin-wide warming is important for these key regions for forest fires, or for Southeast Brazil, the South Tropical South Atlantic, the role of the uncertainty of that driver, how it can very strongly drive the precipitation changes over this region. And of course, with this method, we can show you a different storyline of the future rather than the multimodal mean, where these different driver responses are mixed and giving you a mixed picture, rather than you can go with a consistent dynamical understanding of that region. You can go and see that if a certain way the drivers evolve, then what could be our possible future. So in that note, I would like to say thank you for listening this talk in the webinar today. And now I would like to now Julia will add some more perspective. Maybe Raed can, I give it back to Raed.
Yeah, so thanks a lot, Rohit, for this very interesting talk. There are already a few questions in the Q&A. I guess you can see those. So you can, I think, already answer by text, and we can come back to the unanswered question at the end of the Q&A section. So now it's my pleasure to introduce the second speaker of today, Julia Mindlin. So Julia is a PhD candidate at the University of Buenos Aires, working with Carolina Vera and Ted Shepard. She applies the storyline approach to explore uncertainty in large-scale circulation changes in the Southern Hemisphere and associated regional impacts in South America. Julia is also co-chair for events organized by the Youth Earth System Scientist community and involved in the WCRP Lighthouse Activity Climate Risk, part of the Argentinian hub. So please, Julia, the floor is yours.
Thank you very much for this introduction, Raed. Thank you, Rohit, for that very nice talk. So I'm going to share my screen and support a little bit what I will say with some visuals. So what I'm going to do is try to put Rohit's work in a broader, well, give some perspective on the storyline approach and point out some of the things that are really valuable from the work that Rohit showed when thinking of impacts. So to start, I'm just showing here the different sources of uncertainty that we have to deal with when we want to study climate change, and in particular regional climate change. So the storyline approach is a useful approach to deal and disentangle, to deal with these uncertainties and disentangle each of them and their role. So on the one hand, you might be familiar with the uncertainty in radiative forcing, which is of a social and political nature, because we don't know how we will manage to control our emissions. And that's dealt with by defining different scenarios and testing how the climate responds under a different set of scenarios using global climate models. But then we have the uncertainty in the response to that forcing, and that's the uncertainty in the climate model responses themselves, which have problems not only answering what the level of warming will be under one same emission scenario. They also have a lot of issues simulating different aspects of the physical response in terms of large-scale circulation, and that translates into huge uncertainties in precipitation. So basically what Rohit was showing, right, that these models can show us even different signs in the precipitation trends in one same region. So that's normally related to uncertainty in circulation. And then finally, we have the uncertainty, which is natural and internal climate variability due to the climate system being very complex, the atmosphere being chaotic, and so on. So in particular, the storyline approach is very useful to deal with this type of uncertainty, the model uncertainty, which cannot be treated probabilistically because when we aggregate and use just the model ensemble mean, we're covering potential large risks. But to bring this into a more broad context, the storyline approach is not only used to understand long-term changes, as we just saw. It's gained a lot of popularity over the last years, and to show this, I'm showing a figure from the chapter 10 of the last IPCC report, and this chapter has given the storyline approach a lot of attention because of this capability of showing and representing uncertainty in a very transparent way. And in particular, when we're interested in understanding impacts, we have several questions that we might want to answer with the storyline approach. So these are just two types of storylines. The first one is an event storyline. So this is different from what Rohit showed. And with this type of storylines, what we can do is create a specific simulation in which we reproduce the exact same dynamical conditions that were responsible for an extreme event, and we can change the level of warming, so the warming level in that simulation, to simulate a counterfactual world without climate change and a counterfactual world or a future world with a certain level of warming, and we can address how that specific event could be or could have been without global warming or with a specific warming level. And this can be very useful to communicate, to engage with stakeholders, to explain how climate change can affect a specific known impact. So it not only makes the uncertainties more clear, it also helps engagement. But then on the other hand, and just to show what Rohit very nicely explained into the same framework and context, the causal network below, the dynamical storyline, is showing this approach. And I want to point out that, as I was saying before, one of the sources of uncertainty in the climate change problem is the climate forcing. But that's also entangled with the uncertainty in climate sensitivity. So what will be the level of warming under a given forcing? So that with the storyline approach can be addressed by setting a specific level of warming. So you might have noticed that Rohit's results were expressed in terms of levels of warming. So we have storylines provide an idea of what the millimeters per day change will be per level of warming. And when we do that, we can express our results independently from the specific scenario, and we can address the uncertainty in by what time horizon we will reach what level of warming in a separate way, separating it from the uncertainty in the dynamical conditions. So that's very useful as well when trying to engage stakeholders explaining uncertainty. And finally, I would like to point out that another useful aspect of the storyline approach. So Rohit showed with the same remote drivers and the same storylines impacts in different regions. So in the Maritime Continent, in Africa and South America. And I'm illustrating this with a figure of my own paper. This is not just to promote my work, but it's because it's very clear to the point that I want to make. So here I'm showing storylines with other drivers and for the mid-latitude. So this is very different, but what you can see is that we are showing in each row the precipitation responses under different storylines for 3 different regions. And what's interesting here is that although we have this large uncertainty and we have to represent the change in terms of storylines, what we can say is that the changes that occur under for one region under one storyline, so in one row, will occur together with the changes in the other 2 regions. So that helps us understand correlated risks or risks that could occur at the same time. And if we're preparing an adaptation plan that might involve, for example, investing in 2 different regions or changing our the way that we obtain our crops in Europe or whatever the question is, we can prepare an adaptation plan for each of these storylines in example. And what we would be sure about is that the changes that occur in one region are correlated with the changes that we're reporting in another region. And I find that very interesting because if we look at uncertainties in each region separately, and we express the uncertainty just as a spread around the multimodal ensemble mean, what we cannot do with that approach is address how the risks in different regions are correlated. So that the the consistency in the remote driver approach to produce storylines might be very helpful for adaptation when more than one region needs to be considered. So that was all I had to say, and I'm also happy to answer questions.
Okay, so thanks a lot also, Julia, for this very interesting complementary section to Rohit's presentation. So as you can see also, Julia, there are questions in the Q&A, so maybe you can also,
yes,
if there are ones specific to you, you can answer them. But in the meanwhile, I think, Rohit, you already answered.
I just answered the first, but I didn't want to make the viewers go away from Julia's part. So yeah. I was thinking that maybe me and Julia can both address them together. So I just answered this data related questions of the bias corrected simulations that Harilav shared. That's very thankful to him that, yeah, so this analysis are not with the bias corrected data. And as you have mentioned with CMIP 6, there is not yet so many models still with the bias corrected data, but more with the CMIP 5 or maybe bias corrected data for around 30 GCMs. Okay, so for CMIP 6 is also there. So, but yeah, I would try them out with those bias corrected data to see how it changes or if there is any change in these storylines. And thank you, Malcolm, for that. And the question was from Malcolm is the storylines provide an alternate way. Then the question is, we have SSP, RCP scenarios, and I'm a bit confused as to how these storylines would map to these SSP, RCP scenarios. Or provide more simplistic approach. So yeah, so here the storylines are with those SSP scenarios, I think in the CMIP 6. I'm not sure like how it would relate. The RCP scenarios were in the CMIP 5. So these are like basically showing you the connections with those drivers and that we see in the CMIP 6 runs. So with the different level of warmings, and here as Julia was mentioning, and we do is we scale the responses with respect to the global warming. So kind of they are independent of those different level of warming, or just showing you per degree of warming how the responses are based on per degree of warming. And so we separate the thermodynamic part, which can come from the thermodynamic effect of different level of warming in different models, from those driver-driven responses in those models. So yeah, so that's kind of a way to look at it. But yeah, if Julia wants to tell something about it, then
yes, what I would add is that behind expressing the changes under each storyline as a change per level of warming is the pattern scaling assumption. But the pattern scaling assumption seems to be quite good if we're dealing with transient climate. So if we are under an SSP for RCP 4.5 or 8.5, the changes per degree of warming will be more or less the same. If you look at individual model, the ensemble mean, and then you can address the uncertainty in the level of warming for a given time horizon separately, and combine plausible levels of warming under different scenarios with the dynamical storylines and produce a final storyline map.
Yeah, and if I may add, I wonder your opinion, Julia, because I thought it was quite interesting, this causal network that you had in your presentation, and in there you allowed nodes to be explicit with respect to socioeconomic conditions, right? So you had some kind of a vulnerability node, if I remember correctly. So yeah, in a sense, maybe this a bit stratify or separates between potential drivers. And if you follow a causal network approach to it, maybe there are ways also to tweak things. So you can potentially, the same way that you're troubleshooting, let's say, dynamical driver, you can also troubleshoot a vulnerability node in your system, right?
Yes, exactly. And I'm not too familiar with the social and political aspects of the SSP, but I imagine that if you are trying to understand a given SSP, you can relate some vulnerability and exposure aspects that are consistent with that SSP scenario, and then address the warming levels plausible for that scenario. So even with the causal network, you can introduce the social aspects in those vulnerability nodes that you were mentioning. And of course, one more thing, the two causal networks that I showed are in the IPCC report, but the whole idea of the storyline approach is that every researcher engaging into a scenario-based approach can produce their own causal networks, and then this, of course, are not fixed nodes, are not the only nodes. So land use change, any other node could be included.
It's so I hope the question is more or less answered. If there are more clarification needed, please type in the Q&A box. So now I will switch to the other question that we have there from Matteo Mastropiero. So I think this is directed towards you, Rohit. Well, thank you for your presentation. Very interesting. You considered the box in the Western Pacific, but this resembles both ENSO and global warming. So yeah. So you know it better. BWEP, probably it refers to an acronym in your presentation. So it says this resembles both ENSO and global warming. Do you think it's meaningful to consider EOF1 and EOF2 in your MLR framework to disentangle these two dynamics?
Yeah, so the question, part of it, like regarding what we were talking, that of course there is a response of the global warming. That's why we are scaling with the global warming, the changes, and those EOF1, EOF2 was regarding the variability in that region, how the variability links to the maritime continent that I was trying to show. It just was an indicative of showing that how these regions relate. And then next I moved to talking about the climatic changes in that region. So the climatic changes in that region was scaled with, so it was divided with the change in the global mean surface temperature to capture the parts to relations with respect to the dynamical changes in the precipitation and to separate it from the global warming changes. So in the MLR framework, these two drivers that I include is showing the climatic changes of in that framework. But of course, the figures that I was showing for precipitation with respect to the changes in the variability in the EOF was from an MLR. So it's also putting the PC1 and PC2, it's in an MLR framework. But of course, I didn't divide with the changes in the global mean surface temperature in each time step in the observation. So that could be one way that I can separate the signal on those time series. So just SST signals, when I take on the observations, it could be also divided with the each time step GMST. So then we can get more pure response from those drivers for the observed period. But for the climatic changes, it was mostly clear that we were dividing with the GMST to separate the thermodynamic response, which you can just multiply that each level of warming for 1 degree of warming. This is the response if we want to see at 2 Kelvin GMST warming, 1.5 Kelvin warming, we just multiply the pattern with that and then we get that. But under a certain scenario. So in other scenarios, maybe the warming rates will be different and maybe the response patterns might differ if you go for more another realistic scenario, which I would like to look also, that if those responses has a different amplitude for per Kelvin warming for maybe SSP 585 right now, present situation is not realistic. Future, we are all trying to take an action. So maybe a middle situation of other SSPs could be also interesting to see how it changes. Yeah, so that was the question, I think, from my side, and maybe, yeah, if Julia wants to, or it's fine, yeah. Then, yeah, you have this question?
Yeah, I had a small question that is a bit related to the previous question. So you always were separating, well, at least you were identifying two particular drivers, I think, common to your storylines or common to the three regions. ENSO was there and some kind of other extratropical sea surface temperature region was also a driver. So you had the TNA and the case of...
I tried to keep all the drivers within the tropical subtropical region, which mainly, so one driver was like ENSO region is like, we know from observations that it drives all the parts of the tropical and also subtropical region. So I kept the basin-wide Equatorial Pacific, which is kind of the correlated driver. So it's can bring correlated connections that Julia was mentioning. So, and then there will be some driver which would be important for that region that we know from historically, like for, you know, for Africa, I moved to tropical North Atlantic. It's just a tropical region just below those places for cacao production. And for South America, Southeast Brazil, the SST just beside that place. So the uncertainty there would create some.
Exactly. So this a bit helps my question. So there are also evidence that ENSO yeah, given that it's such a dominant phenomena, is influencing those regions. And then once you had this stratifying of the storylines, you find different setups. So in one case, warming and cooling in the TNA or in the subtropical. So my question is, does this mean that in the CMIP6 we see different degrees of coupling between ENSO and the other regions, TNA or the subtropical South Atlantic? And could you maybe have a hypothesis why this is happening? So basically, how I understand these different storylines is that the coupling in the future is potentially changing or uncertain between ENSO and neighboring regions. So can you maybe comment a bit on this? Well, Rohit and Julia.
Yeah, first, right now, the regressions, the coefficients, what they are showing is, what I understand is the consistency among them. So it's like different drivers have changed in different magnitude in future from the present or from the past. So they changed. So the suppose basin-wide Equatorial Pacific has changed in different levels in different models. Why they did a change in different levels? There could be many reasons, dynamical reasons. That is, maybe in future we can find more into the oceanic factors and how the oceans are inside and how they are changing with the winds on the top, how those uncertainties led to this uncertainty in the SST. So that's another section maybe for the ocean interested people to explore. But right now we see that with regard to this uncertainty, what is the consistent changes? So the uncertainty in those in the region that we are interested, what part is consistent? So if basin-wide warming changed less, then that certain region shows less change, and then other region shows more change. So that consistent part comes from this MLR framework. It captures the consistent connections. But of course, there could be possible that the response itself is maybe different, as the part that you are mentioning, that some model might be more strongly responding, some models. So that's another part. So it's always our framework has, this framework has captured a part of the uncertainty. So there's a full range of uncertainty. For Maritime Continent, I capture 20 to 30% of the uncertainty. So there is a large uncertainty that's unexplained. And that unexplained part can have those relations that like different model has different. So it can come under the model physics that different model has a different compulsion to connect in different ways. So some models might connect in more strongly, some models might connect in less strongly to the region. But that's a total unexplored part of the uncertainty. So here, like we are trying to explain, we just find the consistent part. So it's just showing what these models are showing consistently about among them.
Okay. I'm afraid that we come towards the end. So I'm sorry, maybe Julia had something to add, but yeah.
That was a great answer anyway.
Okay, so then we would like to thank both speakers today, also CMCC for hosting this seminar. And yeah, with that, we come towards the end. So thank you all for attending.
Thank you.
And yeah, good evening.
Thank you.
Thank you, Raed, for hosting and conducting this session.
Sure.